Hi everyone. This lecture is going to be a short one on some simple concepts behind error and error analysis. Hopefully this will be new to nobody in the class, but just in case, here's a brief introduction, get everyone on the same footing. The three main topics are going to be error, its measurement and quantification, methods of describing data, and then using significant figures appropriately. So error comes in two forms, systematic and random. Systematic error is error that is a result of technique or tools. For example, if a thermometer is always 3 degrees higher than what we suspect the actual temperature might be, then we're experiencing systematic error. Now, for example, we can discern the systematic error by having a prior understanding of the system we are measuring. If we know that ice has to be at most 0 degrees Celsius, but our thermometer continuously tells us that it's 5 degrees Celsius, we know that there is systematic error in our measurements because our tool is consistently overshooting the temperature, which is systematic error. Random error is a result of noise in the system, and random error cannot be corrected for except by taking repeated measurements and then correcting for it in our data. So if we measure ice 2 times and the first value is -2 degrees, the second value that we get is 2 degrees, we're likely experiencing random error. We know that it should be 0, but all of our actual measurements are going above and below 0. But if we take the average of these measurements, we arrive at what we expect to get. For most systems, there will be both kinds of error present, both systematic and random error. And this makes it important to understand the system that we're measuring and also to take repeated samples so that we can, if we understand the system, we know if we're experiencing systematic error, and if we take multiple samples, we can reduce the noise in our data and get better, more accurate results. In order to quantify the error in the measurements we're going to be making in this class, we're going to be using the percent error formula. The percent error gives us the relative difference in the measured value and the expected value. A lot of people will use the absolute value of the percent error, making it an always positive value. However, I prefer not to do this because it can take away some important information. For example, a -% error tells us that we're consistently lower than our accepted value. So we can know to account for this when we're taking our measurements or making our analysis of the device. And then how to describe sets of data, we usually use the 3 basics here, mean, median, and mode, where mean is the arithmetic mean, not the harmonic mean or anything, just the standard good old mean that everyone already knows how to calculate. The median, or the central value of an ordered set. If our set is disordered, you cannot find the median. Everything has to be in order, ascending or descending. And then the mode, which is the most commonly appearing value in a set. These should be very familiar to everyone. I'm not going to go into too much detail about these. I just expect that you should know how to do it. And then a fourth very important value is the standard deviation, which is a measure of the variation in the data or how tight our normal curve is. A very sharp, narrow peak has a small standard deviation, and a very wide, flat curve has a very large standard deviation. So it's important because it tells us if our value is reasonable or not. And in a normal distribution, which almost everything is, 68% of the data will lie within the range of 1 standard deviation from the average. And 87% of the data will lie within 2 standard deviations, and so on and so forth. As an example, if we know that we have an average value of 3 and a standard deviation of 1, if we take a measurement and a value comes out 8, we know that it's an extreme outlier because 8 is 5 standard deviations from the mean. Only 1 in 1,744,278 values will be 5 or more standard deviations from the average. So if we get something that's 5 standard deviations away, we know that something has gone wrong, or we've gotten very unlucky. Or lucky, depending on what the experiment is that we're running. And then finally, significant figures. Most of you should know this already, but just so that everyone is on the same page. The number of significant figures indicates the precision of the data, and it's limited by our tools. If we have a digital multimeter that can only give us 4 significant figures, that is our accuracy. You cannot go beyond that. You can use less, but you cannot have more than what our tools allow. In using them, do not reduce significant figures until you've completed all of your final calculation. Maintain all of your variable lengths until you're done with your calculations, and then trim there. Trailing zeros count as significant figures, but leading zeros do not. And integer values typically have infinite precision. So like I said, this was a short one, and that's all for now. Thanks for listening.